Today's video starts with a famous and probably apocryphal story about the mathematician Carl Friedrich Gauss that goes something like this. Gauss was 9 years old and sitting in his math class. He was a genius even at this young age, and as such was incredibly bored in school and would always goof off and get into trouble. One day his teacher wanted to punish him for fooling around and told him that if he was so smart, why didn't he go sit in the corner and add up all the integers from 1 to 100? Gauss went and sat in the corner, but didn't pick up his pencil. The teacher confronted him, saying, "Carl, why aren't you working? I suppose you figured it out already, have you?" Gauss responded with, "Yes, it's 5,050. The teacher didn't believe him and spent the next 10 minutes or so adding everything up by hand, only to find that Gauss was right. So how did Gauss find the answer so fast? What did he see that his teacher didn't? The answer is simple, really. It's all about pattern recognition. Let's look at a simpler version of this problem. Let's consider just the numbers 1 through 9. Pause the video here and take a few moments to add these up. But don't do it the boring way, one by one from left to right. Try to be creative. Look for patterns. What is the fastest way to sum this series without a calculator? My own students often come up with two different but related approaches. The trick is to create pairs that sum to 10. One way students do this is to write the numbers backwards underneath the original series. Then we see that the columns sum to 10, and how many columns are there? 9. So 9 times 10 is 90. But that's double what we need from the original series. So divide that in half and we get a sum of 45. The second approach is to pair numbers that sum to 10 within the series, pairing 1 with 9, 2 with 8, 3 with 7, 4 with 6, and 5 with itself. How many pairs of 10 are there? 4.5. So 4.5 times 10 is 45. Let's try to verify Gauss's answer of 5,050. Can we use these same findings to find the sum from 1 to 100? Pause the video here and try it out yourself first. Let's create pairs again. Only this time they won't be 10, instead they'll be 101. And how many pairs of 101 are there? Well, if you like method 1 more, we would have 100 pairs, but that is double what we need, so we need to divide by 2 to get our total of 5,050. And if you like method 2 more, we could have 50 pairs, which also gets us our total of 5,050. Now that we've found a pattern, can we generalize it? Take a moment to think about what each part of these expressions represent generally, and try to write out your own formula. If you liked method 1, your formula might look like this. Sum the first and last term of the series, multiply by the number of terms in the series, and divide everything by 2. And if you liked method 2, your formula might look like this. Sum the first and last term of the series and multiply by half the number of terms in the series. Either way, these formulas are mathematically equivalent, and when using sequence and series notation, we write them like this. So why does this work? Well, these series are what we call finite arithmetic series, and their defining characteristic is a common difference. Meaning to go from one term to the next in the series, you always add or subtract the same value. In both of the series we looked at, that common difference was 1. And that common difference is what really is key here. Without it, we wouldn't be able to pair all these numbers the way we did and get the same value each time. So we just learned how Gauss, allegedly, outsmarted his teacher by quickly summing up the numbers from 1 to 100. He recognized a pattern and used it to get his answer in seconds instead of slogging through the arithmetic one by one. But knowing this trick isn't just about impressing your teacher. Some of you may have heard this puzzle before. Jeff Bezos is feeling charitable and decides to give away some money, and you are the lucky recipient. He presents two options. 1, an upfront $1 million, no strings attached. Or 2, a slow payout, where in the first second you get 1 penny, then the second you get 2 pennies, and at 3 seconds you get 3 pennies, and so on and so forth for a whole year. Which option should you choose? Put your guesses below, as well as your guess for just how much money option 2 might accumulate. Now, option 2 is a finite arithmetic series. Its first term is 0.01, 1 penny. Its common difference is also 0.01. and the number of terms in the series is the number of seconds in a year, 31,536,000. The last value we need is the value of the last term. We need to know what the payout is at the 31,536th second. Finding the last term of an arithmetic series is actually quite simple. There's a nice little pattern here too. If our first term is 0.01 and our common difference is 0.01, then our second term can be written as 0.01 plus 0.01. And our third term is 0.01 plus 2 times 0.01. And our fourth term is 0.01 plus 3 times 0.01. So we can see each nth term is 0.01 plus n minus 1 times 0.01. So the 31,536,000th term then is 0.01 plus 31,535,999 times 0.01, which is 315,360. Now we can calculate the sum using the formula we developed earlier. We get nearly $5 trillion. Clearly the winner over $1 million up front. Unless you're unwilling to wait a year, I guess, or you have some insane investment strategy that could turn $1 million into more than $5 trillion in only a year. But what if instead of upping the payout every second, it was only every minute? Still think we'd reach over $1 million in a year? Let's see. By changing the payout to 1 cent every minute, we instead have 525,600 minutes in a year, and our final term of the series would be 5,256. That makes the sum over $1.3 billion, still quite impressive. What about every hour? There are 8,760 hours in a year, so our final term would be 87.6, and the sum would be less than 400,000. Still a decent amount of money, but less than $1 million. So at this point, we should just take the immediate $1 million and run. So was your initial hunch correct? Did you ever think that over a year you could turn pennies into nearly $5 trillion? And that's for something whose sequence grows linearly. Just wait until we talk about geometric series. Their growth can literally be exponential.
Thank you for watching. Please subscribe and share our videos. Be sure to follow Math the World on Twitter, Instagram, and Facebook. Thank you so much for your support.